Hi, and welcome to the Mentored Engineer. In this video, I want to explain how to use our hydraulic cylinder calculator. It's a fun tool, get you ahead on what you can and cannot do with a cylinder quite quickly. So here it is. Let's get started. First thing we're going to do is go to mentoredengineer.com, and you can either find it under Resources and Calculators, or you can take a shortcut and do Cylinder Calculator. And okay, so we're going to click there, and it's just going to ask us some basic information about our cylinder. I'm going to pick a generic cylinder. I'm going to use a 4.5 inch OD, a 4-inch bore, 2-inch rod, and it gives you the opportunity to use a hollow rod. If you don't have a hollow rod, if it's just a solid shaft, just leave it blank. I'm going to say that my stroke is 36 inches long, and my retracted length is going to be, let's just say it's 48 inches long. So that's all the specifications of the cylinder. Now the system info is something that adds a little bit more dynamic to our problem here. So we're going to extend the cylinder. We want to know what our flow is, and I'm just going to say it's 6 gallons a minute and maximum pressure of 3,000 psi. And I'm going to say that the retract flow is also 6 gallons a minute and 3,000 psi. Now this might not be the case in all circumstances where I may have reduced pressure extending because I don't want to buckle the cylinder, or I may have reduced flow rate in the rod side. One reason or another, it just retracts you fast or whatever else. Okay, then I got some cool options here. The first is a regenerative circuit. Now, a regenerative circuit is when you put oil into the base of the cylinder and you also pressurize the rod side. Now, most people think that this probably does nothing, but what actually happens is you have the rod diameter that's different on one side or the other. So the cylinder will actually extend, but what happens is the oil from the rod end comes back into the bore extend side cavity, and will actually extend it much faster than your flow rate will allow. All right, so if you check that, it'll do the calculations for you there. The other thing is support from buckling. So if you have a traditional cylinder where it's pinned at both ends, you can hold the middle, the end of the bore, to prevent it from buckling, and that'll improve your buckling strength. So if that's your case, go ahead and do that. If you have a trunnion mounted cylinder where it pivots near the barrel, the end of the barrel where the rod starts sticking out, and you're holding the base end, it'll also work in that condition. And then there's a third option here of an external load at full extension. Now this is a situation where if you had, it's popular in aerial lift devices where you have a lower boom that goes over center, and suddenly you switch from a compression load when you start lifting it up, and all of a sudden it's in tension and you're trying to pull it back. You want to make sure that the weight of the boom and all the stuff on top, plus trying to extend that cylinder, doesn't pull that cylinder apart. So if we have an external load at full extension, we want to know that, and we click that button, and then we can add in our load there. Okay, so we're going to ignore all those for right now, and we're just going to come down here. And the last section is we want to know the barrel strength of our material and our rod strength. So we have 70 KSI, and let's just say 100 KSI for our rod. And those are pretty good answers for professionally designed cylinders. Okay, so let's go and look at the results here. We have a hydraulic area of 12.57 inches extending and 9.42 retracting. We have cylinder volumes here as far as difference between extending and retracting. How much oil is it going to contain? So you can see the volume difference here is 113 inches cubed, or half a gallon. So we need to make sure that our hydraulic tank can handle that disparity. I recently designed 2 cylinders where they had each of them a 22.5 gallon difference. And that actually required a very large hydraulic tank, and we ran into problems implementing that simply because of that reason. Okay, so since we have the flow rate and the volume of the cylinders, we can also determine how long it's going to take to stroke that cylinder one complete stroke. So 20 seconds out and 15 seconds back. So that may be something that we would want to adjust. Here tells us how much force we can put out, both extending and retracting at that pressure. And then we have our return flow. So every cylinder, when you pressurize one side, you're going to get different flow out of the other side. So when I'm extending my return port, the retracting side, is going to have a lower rate because I'm putting more oil in and I have a larger area, but a smaller area coming back. So that usually isn't the case that we're concerned about. It's when we're retracting and how much flow we get out of the extension port. And in this case, it's 8 gallons per minute right here. All right, so we're putting in 6, we're getting 8 out. That's pretty cool. All right, so then we want to find out what size cylinder we should have this at. And this is based on a 20 feet per second orifice, basically, that we're trying to get oil through at 20 feet per second. All right, so our extend port here needs to be 3/8 of an inch. Our retracting. So what we want to do is pick the bigger one for each one. So on our extend port, while we're retracting, we should have at least a 1/2 inch port there. And we also want to have a 3/8 port on the retraction side here. Okay, so I kind of glanced over this earlier, and it's the area ratio between the two sides of the cylinder. So on one side I have the bore squared, and on the other side I have the bore squared minus the rod squared. All right, and we ratio those to each other and we get 1.33. It also calculates our extended length, the dead length of the cylinder, and that's basically the unusable length of the cylinder. So I have my rod ends on each side, and then I have a retracted length of 48 inches, and I have a stroke of 36. So the 48 minus the 36 is the dead length, and that would be 12 inches. All right, now we're going to get into structural components of the cylinder. We have our bore cross-sectional area, and that's the structural tube that is identified by the barrel OD and the bore diameter. And that gives us 3.34 inches squared. We have our rod cross-sectional area, and that's 3.14 inches squared. It gives us our critical buckling load and our buckling design factor. All right, so this cylinder right away should not be used in compression at full stroke. All right, and if you look at it here, my force is 37,700 pounds, and my critical buckling load is 31,895. All right, we can look at our burst pressure of our cylinder based on the 70 KSI tubing. That is 8,200 PSI. Our hoop stress is 2,500, and our axial stress is 51,000. So you add all these together, and you get the combined stress of 57,000 and a design factor of 1.23. So this cylinder, for its load at full pressure of 3,000 PSI is not a good fit. 1.23 is not a good design factor. So we can do several things. We can lower our pressure. we can look to increase our area of the outside bore, so maybe going up a 1/8 of an inch from a 1/4 inch wall to a 3/8 wall would make a big difference here. All right, so there's a lot of things we can do there. We can also up our material if you can find something. All right, well, I'm glad you watched this video, and we hope it's useful to you. Thank you for watching The Mentored Engineer. Happy designing.